All right, so let's go into the first slide. What's the agenda for the day? The agenda for the day is making the distributed systems great again. And we have our very own Alfred, who is, in with the team. He's always part of all my. I'm a big Batman fan, so he's always part of all my slides. Little thing about me, like I said in the beginning, I'm a principal estate from um, search team. I've been at SecureWorks for a year and a half. I'm from India, and I'm also that like the slide says, Tamil, or that's the culture where I'm from. And today happens to be the Tamil New Year's Day. So if anybody on the call who celebrates Tamil New Year's Day, a very happy Tamil New Year's Day to you. And hopefully this year is going to be so much more better than the one we've had last year. I've been in the industry for 11 years now. I've worked on three major domains, like I would like to call it, e-commerce for about 2 years, and then cloud computing for about 5 to 6 years, and then landed headfirst on InfoSec. This is my second InfoSec job. I was in a startup previously, worked there for about 2.5 years before they got bought out, and I was looking for a change, and I'm so glad that I landed at SecureWorks. This has probably been the most technically competent team that I work with, and people are very receptive and generous with their time and also opinion and feedback when I seek them. So thank you all for that. I'm really passionate about automation. Anything with respect to scale, performance, DevOps and SecOps is my forte, I would like to think. And I always believe I'm just scratching the tip of the iceberg in whatever I work. So I'm always open to learning. And if you all have, as you go through the slides, any specific content that you think I did not cover very well, or if you have feedback, please feel free to DM me or email me in any messenger goat. Whatever you feel is appropriate. I'm open to getting feedback on that. Uh, now related to the talk, the reason why we are here obviously is because I have 7+ years of experience in distributed system developing and testing. So I would like to at least share my lessons learned and hopefully get some feedback, and somebody can point me to something interesting that I've totally missed. I'm also a blogger. There's that website you can probably look up. I do technical blogging, and I'm also a big finance nerd. So if you're interested in market theory, economics, mean reversion, or stock trading or options trading, if any of that makes any, is interesting to you, you can DM me on Mattermost as well. And like I said, that's another learning opportunity for me. I've been doing that for 10 years, but again, I'm always open to learning something new. I'm also a wannabe stand-up comedian, and we have a Siva stand-up jokes in Twitter and LinkedIn, and also we have a comedy channel in Mattermost. So if you're having a really bad day or really stressful day, hopefully that can give you some relief. And yeah, and feel free to you can all also join the comedy channel, because we have been doing a lot of collab comedy, meaning somebody gives me an idea and then I try to add humor to it, or you can just post your own jokes in the comedy channel. So feel free to check that out on Mattermost. And most importantly, I'm a father, and this is Simba. We got him last year, and I'm so glad we did. We got him pre-COVID, and my wife and I, we survived COVID just because of Simba. So yeah. And finally, I have my Twitter and GitHub handle. Feel free to check those out. Let's get into the meat of the talk. What is a distributed system? Now, Wikipedia defines a distributed system as a system whose components are located on different network computers, which communicate and coordinate their actions by passing messages to one another from any other system. So to say that in a different way, you're trying to accomplish something as a software, and you're trying to share the workload. And the biggest USP, in my opinion, at least what our distributed system accomplishes, is there is no SPOF, meaning there is no single point failure. You try to have the workload replicated between, I don't know, different container. I mean, you can have a distributed systems in a large sense in terms of applications deployed in different data centers, or if you have HA pairs even available to our Kubernetes pods running in a single kube cluster, even that is distributed system, in my opinion. It's about how you implement the core essence of the idea, right? And yeah, so that's what a distributed system is. Going on to the next slide. So if for anybody who's worked on distributed system, they might be aware of something called the CAP theorem. And this is, in my opinion, the cornerstone of or at least gives you a very foundational both exposure and also what are the basic fundamental tenets that you would need to follow when you're doing when you're developing or architecting any kind of distributed system. So in CAP theorem, I'm just going to read out what the wiki says. In theoretical computer science, the CAP theorem, also named as the Brewer's theorem, he's a scientist, after the scientist Eric Brewer, states that it's impossible to have a distributed data store to simultaneously provide more than two of the following three guarantees. So think of these as the three possible features or facets, or what you're shooting for in a distributed system. And CAP theorem says you cannot have more than two at any given point in time, meaning a system cannot be consistent, available, and partition tolerant, all three at the same time, or strong consistent, I should say. So let's dive into each of these a little bit more in detail. So let's talk about consistency, right? So when you're developing a system, let's take an example. Let's say a company like a company A wants to build a ticketing system, and their complete model is based on having exceptional support, where the SLA is, like, I don't know, like less than 10 minutes or something. When customer opens up a ticket, no matter what tier they belong to, the company guarantees that they would have somebody respond to the ticket in like 10 minutes. And let's say they have, like, I don't know, maybe 10K customers. So you can see if they are a cloud computing provider, or even a SIM platform like us. A lot of it can depend. A lot of the success depends on how fast or how efficient the support model is. So they had an awesome architect. Let's say in this case, it's our very own Cliff James. He comes up with a model where he says, okay, I need to make sure that this system is fault tolerant. It's not going to fail, because the top and bottom line of the company depends on the revenue numbers. I mean, the success of the system. So we start developing a distributed system, meaning we are trying to shoot for the same code base or the app being deployed in multiple data centers. Now, let's say for argument's sake, the data centers are going to be A, B, and C. Just to recap, a company is developing a ticketing system, and they are trying to do it globally distributed, and they have the ticketing system deployed in data center A, B, and C. Now, the first point of consistency would be, is it going to be strong consistent, or eventually consistent? And this is probably the first question you would need to answer yourself if you're trying to architect or develop a distributed system. The reason being, this can have a lot of ramifications down the road. Case in point, your how you handle your replication, how are you going to handle fault tolerance, and also in terms of development, what's going to be your data model. A lot of things can depend on this fundamental facet called consistency. So in essence, what it means is, let's say your app is deployed in data centers A, B, and C, right? If you claim your app to be a strongly consistent app, that means at any given point in time, when you do a API read, or when you try to read something from the system, let's say in this case, we are trying to read a ticket by ID, right? A strong, consistent system guarantees that the read data will be consistent across all the data centers where it's deployed. So no matter what happens in terms of in the background, the system is architected to handle the incoming traffic or the incoming mutations in a way where the resource, when the read happens on a resource, it's the same across all the data centers. That is strong consistency. Eventual consistency is when the mutations happen in different data centers. Let's say in this case, we have an eventual consistent system, and we have a ticket, I don't know, ticket ID 1, right? And a support person comes on, uses the UI, which internally is pointed to, via the API is pointed to data center A. If they make an update on ticket, if it's a strong, consistent system, the next minute or the next microsecond or whatever, when somebody reads the ticket, it will be the same in data center B and data center C. However, if it is an eventual consistent system, there is something called the origin of the change. So when a support person were to update the ticket using the backend pointed to data center A, or your data store pointed at data center A, you would update the ticket, and the subsequent read on the origin of the change will always have the same information of the ticket. Meaning, I update the ticket in data center A, I come back and look up the ticket by ID in data center A, I'm seeing what I'm expecting. However, if somebody else, across the pond in Europe is probably going to, look up the ticket and they're pointed to data center B, there's going to be a delay. And that delay is what the word eventual stands for, is that the system is architected to eventually catch up on all the changes that are coming from the origin data center or the origin app where the change or mutation has happened. right? So in eventual consistency, it presents itself with unique challenges because, like I said, the change happens only in one of the DCs. So how is the system architected to handle state replication? Meaning when things change, when the system of record, which is your, say, your data store, changes in terms of the values of the thing we care about, how is that information replicated across all the different data centers available? And what's a quorum? So let's say in if you've used something like Cassandra, which is a time series database, there's a replication on write, which means you write something and that gets replicated. And Cassandra won't give back a response until depending on the way you configure it, like certain number of nodes have the data, have the updated version of the data, and then the application layer gets a thumbs up from the data store saying, hey, I have persisted what you've given me. So my point being, you have to take into consideration a lot of different things when you're trying to develop a eventual consistent system. For a strong consistent, strongly consistent system, I can give an example. Let's say you're developing a traditional API with SQL backend like Postgres, and if you have a master slave replication enabled, and you do a write from the app layer to your data store on Postgres, and if you've set up Postgres with the expected settings, the master slave replication would happen out of the box. When that happens, you're, no matter if your slave is going to be the same DC, if it's going to be somewhere else, you can claim that to be a strong consistent system, because any subsequent read on the incoming mutation will always give you back the same data that you've just modified. Some of the architectural considerations that you would need to do, in my opinion, on consistency is, where are you going to handle your replication? Is it going to be at the application layer or the database layer? I just gave you an example where in Postgres, you can push the consistency workload down the stack to the database layer, where you can just have Postgres do the replication, which would take data back and forth, and your application is just provides a entryway into modifying the data on the data store. The other way of doing that can be, your data store are going to be dumb data stores where they get the data from your backend and persist it, and that's it. And you have a layer that sits on top of the data store, which would handle the way things would replicate. So one example that I can think of is, let's say we have a data store and we have a cache. You have a let me think. You have a Postgres database and you have a Redis cache, right? So you don't want for architectural considerations, we make the determination that replication via Postgres master slave is slow. It's not, but I'm just saying, for hypothetically, for this example, let's say that is slow. So the way you would offload that from the data layer to your application layer would be trying to take advantage of Redis. So Redis obviously is going to be in-memory key store. Your reads are going to be much faster. So think of it as where you have Redis in all the data centers that has the Postgres database as well, and those act as cache. You can very easily implement a PubSub model, which would subscribe onto different Redis instances. In Python, if you've used Tornado, it's it exposes. It's very trivial for us to create a backend with like a PubSub, a long polling mechanism. Same thing with the WebSockets that we are moving towards these days with a lot of our CTPX apps. So we can have that model implemented where the app itself will take care of getting the data from one data store to another and not offload the replication onto the data layer. I mean, there are pros and cons, obviously, with everything in software engineering, and that's the same with these decisions as well. And that's why in my opinion, it's very, very critical that the product owner and the architect are in harmony in terms of what they want to achieve, and the product owner kind of like sells the vision very clearly. That way, the architect can make sound choices on what's going to be the different facets of the system. I'm going to move on to the next one. Is there any questions so far, or Tia, should we table the questions to the end?
I'll leave that up to you. I'm sure that we'll have questions at some point.
Sure. If there's any question, please feel free to ping. I'm also having an eye on the on the Teams, but obviously since I'm sharing and I'm on single screen, so if there is anything we can ping, I'll probably go to the next slide. Here is so the next facet of the distributed system is availability. So this is probably the most easiest to grasp, at least for me it was. It's the system uptime. How available is your system? Well, what are the SLAs you have? What is the uptime you guarantee? what are the different considerations you need to make sure that the app doesn't fail over, and it's always available. And like going back to our example of a ticketing system, if you have a company dependent on the support, ticketing is obviously very critical, and if those were to go down, then that affects both the top and bottom line. So what are some of the defensive software architecture decisions we can take from an availability standpoint? We have HA pairs, which is for every app that you deploy, you have a redundant pair. It can be like in HA, that can be a separate topic in and of itself. You have the active pair, active passive pair, where only one of the pair is actually doing the work, and other is just there for contingency purposes. So that is something that we actually do here at SecureWorks. And the next one is observability. Like it's a fancy way of saying I'm going to monitor my app. You can have we do a great job of trying to monitor a complete infrastructure at the data layer, at the presentation layer, and also at the UI, and also at the backend. So that is what basically is, the more the better. And also there are things like, especially in a distributed system, it's very critical that an architect, in my opinion, takes into account what happens to a hop of a data. Like for instance, not only distributed system, any modern software, if you think about it, like in our case, when when a customer makes a request, it hits the API gateway, and then there are multiple hops that happens to the actual request before the response comes back, right? So if that's the case, if you don't have something like a distributed tracing, wherein you're capturing the request from the customer with whatever the tracing schema we use at the source or at the entry point, which would be our API gateway. If we don't track it or stamp that with something like unique there, then if the request were to fail on one of the subsequent hops, there's no way for us to meaningfully say why it failed, or which part of the request failed. So I think we're already doing a great job out of that. So if you've looked at our Datadog dashboards, and also Sentry, so we have those unique labels per app, and that'll give a lot of insight into, like, if something had failed, is this like something that's failing at the entry point, or a subsequent app, or one of the subsystems is not available. So a lot of things. Slow logs in your database. So if you've used any system at scale, you're obviously going to be looking at the database read times and write times. So Postgres, MongoDB, and some of the other database in the SQL and NoSQL databases I've used has a flag that will let you monitor the queries that are slow. So basically, you can define a threshold in that setting. And what the database would do is, if any query, both a read and write, were to exceed that threshold, it would just mark it, flag it, and log it. That way, if you do any monitoring based on your slow logs, if you're a database admin, I mean, you definitely, this is your bread and butter. But for the others on the call, slow logs is something that you can take into consideration, especially when you're trying to a new stack and a new data store, things like that. What else? Sync versus async. So if you're expecting your API to have like a lot of simultaneous consumers at the same time, and maybe a lot of burst spikes in terms of, like, the expected workflow load, you might want to consider an async model, wherein the API is not synchronous, but rather for the initial request, responds with a unique identifier that the consumer can come back to and check what happened to the status. I mean, it's standard of, if you've used Python, like using something like AMQP, where you have Celery, which would, like, it's a distributed task worker, so it would put that on a queue. RabbitMQ is a very popular Python thing. I'm sure there's equivalents in like Java and Golang, any of the modern development frameworks. So once you drop it there, and then you have these async workers that picks them up and does the work and drops the result back onto a queue. So when somebody were to request with, hey, what happened to the request I made? I have this request ID that the system gave me back. The async worker on the background would go monitor the results queue, grab the ID based on, grab the result based on the ID passed by the consumer or the customer, and then return the response back. So in this way, you're able to scale out a lot more and kind of try to eke out or squeeze more out of your, if you have constrained resources. A lot of times, it's probably not a concern for us, but a lot of times in different software setups, you have limitations on AWS cost, or even if you're running things in like, VMware in like a hypervisor, there's like, a hard cap to your cloud cost. So people want to like front load a lot of that in their queuing infra on how much they can handle in terms of like the incoming request. And then they obviously, like, kind of cycle through the set of requests using async technologies. Finally, horizontal and vertical scaling. I mean, this is very self-explanatory. You can either add more of the same or make what you have or expand what you have to be better. So a case in point being, if you have to lift 200 kilograms of I don't know weight, and if you have the capability only to do 50, I can either get four of you or one of a person who's able to lift that 200 kilogram weight. So depend, a lot of things would probably come in. Maybe the compensation that the 200 gram, the lifter who can do 200 kilograms is going to be more, which can be a parallel to your cost can be more in terms of the instances you want to run. Are you using spot instances, or are you using like something that's going to be temporary just for this specific work? But point being, you can do horizontal and vertical scaling, and in Cube we already do that with a lot of our internal CTPX infra. So yeah, if you've been on CTPX for like a year or something, I mean, a lot of this is obviously going to make a lot of sense to you, because we do this extremely well, fairly well. Finally, moving on to the next topic, taking a quick pause. Is there a question? Anyone? Everyone is following with me? Should I slow down, maybe? Talk slow? Any feedback? I'm just trying to
Yeah,
look at the...
a little bit of slowdown would be nice, but
Okay,
this
gotcha.
was
All right.
always also scheduled for 45 minutes, and you have 15 minutes left.
Yes, so I think I'm probably going to take 5 more minutes before I want to open it up to questions. The final thing about the CAP theorem is the partition tolerance, which talks about what happens when one of the nodes in a distributed network were to fail, right? So, like I said, going back to the initial example, we have a ticketing system. We have that deployed in three different data centers, A, B, and C. The change or mutation or the incoming update to a ticket can happen from any of the data centers. So what happens when one of them is off the network, right? Or is not available, is not part of the distributed system anymore. So that introduces what is called a split brain problem. The reason being, when a cutoff like that happens, let's say system B is not able, data center B is functional but not able to talk to data center A or data center C. Anybody making an update on a ticket in data center A is going to see a different version of the ticket to somebody who makes an update on data center B, because that update would obviously be different. So the replication is not happening. The individual components themselves are functional. So when a thing like that happens, it's what's called a partition. And how this specific aspect of distributed systems talks about what should one do to take care of it, like how can you be defensive from an architecture and engineering standpoint to make sure that these kind of things can be avoided. Because in reality, you're never going to be able to have a 100% fault tolerant system, right? Like things are deployed in cloud, things can happen, Mother Nature, systems can catch COVID. Hopefully that's not going to happen, but that's a scary thought. So in a split brain problem, you have the classical question of who's right. Because if the changes were to happen in multiple data centers which are not talking to each other, and I, as a customer or a consumer of the API or the UI, were to like open up a ticket and see a snapshot of its current state, I don't know if that is correct or not. For all we know, once the customer hits refresh, if the DNS routes the request to a different data center, he or she is going to see a different version of the ticket. That can cause a lot of headache and a lot of nightmare, right? So why would this happen? This can happen because of a network fault, or like a disk overload on the actual VM or VMs running the app. The bandwidth could be poor to a specific data center, which means there's a lot of delay in data centers talking to each other and catching up on the state. And yeah, I mean, things are deployed in cloud, which is, as they say, it's not cloud, it's somebody else's computer. So you have a hypervisor, which means you have a classical noisy neighbor problem. Your VMs could be co-located with on the Hyper-V with another app, which might be hogging a lot of like uplink available, I mean bandwidth available, and also CPU and disk space and whatnot. So how would you say if the partition tolerance, I mean, if a partition were to happen, what are some of the things that you could do or think about when you design an app for this kind of eventuality? You can have data store snapshots, which means that at any given point in time you are trying to like let's say you have your data stored in three different or multiple different data centers. You keep a track of all your snapshots of what happens with your data, and then when the system detects that there is a partition that has happened, one thing that has worked for me, at least in the systems that I work with, is it's kind of difficult, but at the same time, it's very useful if you get it right. Is, if you do a multiple way merge on the data. So for the system that I specifically worked on, it was a NoSQL database where um, where the updates were actually point in time updates, which means the actual data being stored is not a complete representation of the object, rather what the object would look like at a point in time, right? So we went with time series data that way. So given that was the case, we were able to do database snapshots in MongoDB of all the data, and if a partition were to happen, we would just compare the data and do a MapReduce, and create a copy that we think is the current copy, and then replicate that over to all the data centers. It was very powerful and very tricky to get it right, but if it does, then you can be totally, you need not, you can sleep better at night, because otherwise things get really hairy, especially for a ticketing system where if things were to go out of sync, and for a team that's distributed all over the world. Using replay. So replay is a fairly simple technique, but it's very powerful as well. It is how, if one of the data centers were to go, if one of the instance of the app in a distributed system were to go out of the network and then rejoin, how would it catch up with the other? How would it catch up with the current state of all the resources? The one way could be uh, prior to, whenever the databases are talking. I mean, the app or apps are talking to each other, the different instances of the app. We could make an architectural decision of storing the metadata about the actual state, which in this case can be, let's say, the timestamp of when database B last checked in with A and C and all its peers. So if you were to have a timestamp like that, then what's going to happen is it's going to give you the ability for the data center that has just rejoined the network after a partition to go and talk to the other nodes, and kind of like have a point of reference of where it lost getting when it lost getting the data, and then you can replay all the data back again. Push versus pull is another model. Like I said a few slides back, if you have the app do the replication as opposed to the database, you can have design decisions of is the originator going to be the one that's going to initiate the peers. So basically, let's think of it this way: when a change has happened, uh, the origin data center would then reach out to the other peers to go, hey, this is the update I've got, go update your states on these resources. Or the pull model, that will be the push model. The pull model would be the peers would frequently check with everybody else, every other peer on the network, to go and get the data. So there's a lot of that can be a whole tech talk in and of itself. There's a lot of pros and cons and trade-offs there, but that is also something that needs to be considered, and that's the reason I put it there, is that you got to be very cognizant of, are you doing a push or a pull model in your recovery techniques. Let's go on to the next slide in the interest of time. So how do you test a distributed system? My current role is a software developer and test, which means obviously testing is of my primary focus, and that's why SecureWorks pays my check. So anything that's distributed, in my opinion, you are signing up for complexity if it's a big enough system. So you cannot have a single tiered approach for testing. So that's why I kind of call it a stacked approach. It's strength in numbers. So this is by no means a comprehensive list or whatever, but this is just that what I would look for when I'm tasked with coming up with a test plan and testing strategy and automation for a distributed system. So at the top would be your functional testing of the API or the microservices that are deployed on the individual nodes. So obviously, the system has to work first, and the test will have to validate the system is working first. So that's your functional testing, and the system would be one of strongly consistent or eventually consistent, right? So how the replication is handled, and the testing needs to be put in place for that, and performance and scale testing for the entire distributed setup. So you need to be, the SDET working needs to be very aware of what the limits of the system are, and needs to have a pretty clear the other conversations with the PO and architect, both in terms of who the intended audience for this app is going to be, and what's the expected throughput and traffic and all that good stuff. If the KPIs are not available, which in some cases they won't be, I think the SDET, him or her, should take the responsibility of doing what's called the performance benchmarking. There are a lot of different techniques, and again, that can be another entire rabbit hole. But the long and short of that would be try to establish a benchmark with what you know is working, and then slowly scale that by factor of 2, 3, 10, 100. Because performance testing at the end of the day is kind of like, it's art and science. I would like to think of it, because you are trying to find the needle in the haystack where the performance goes off a cliff. So to find that, there are multiple different ways you could do it. It's not like as difficult as it sounds, but um, yeah, that is something that's really important, that needs to be part of the way you would test a distributed system. Security testing, we do a fantastic job. Our DevOps team, kudos to them. We have our static code analyzers everywhere. I've also heard that some of the teams are running port scanning and pen testing of their infrastructure. So that definitely needs to be there, and if possible, as part of CI pipelines. Finally, chaos testing. In chaos testing, the idea is what if. It basically answers the question of what if. Like, there can be multiple what ifs in the way you could bring the system down. Chaos testing gives you a formalized way of trying to introduce inconsistencies in your infrastructure. That way you can monitor what happens when the system is pushed to such an inconsistent state. So yeah, this is like the top 5 things that I would always focus on when I'm trying to test a distributed system. Obviously, I've not covered something like UI testing, because my primary focus when I was doing this is backend. But I'm pretty sure that the UI experts on the call would like to say there are like unique challenges there as well. And we've like I said, I'm not including that here, because this I'm trying to focus this as the backend for a distributed system. All right, so I'm just going to quickly run a scenario here just to get the point home, and then have a couple of minutes hopefully for questions. So let's think of the scenario is we're going to build a home. The home is a nice 2-story home in the heart of Hill Country, Texas, right? That's where I'm from Austin, Texas, and that part of Texas is very beautiful. If you get a chance to visit there, please do. So that is what we are trying to build, and I'm trying to draw analogies with or parallels with the software world. Let's say that's the thing we are going to build. And what are the different components or things of interest when we are building a home is obviously the raw materials on the conveyor belt, lumber, bricks, concrete, and all that stuff. You have your supervisors and planners. You have the construction crew who's actually doing the construction, and then you have the home inspectors. Now, again, drawing a parallel, your raw materials are on the conveyor belt, or think of that as your messages, data, whatever your app is trying to store and modify and all that stuff. Your supervisors and planners are your architects and your POs. They are going to set what the app is going to be all about, and they're going to give you a concrete design of this is the intended use case, and these are the complete background information. The construction crew is technically the entire engineering team, who's going to work on taking that plan and go to town with implementing a software based on that. And finally, the home inspectors, I have them listed last, is because those are your estates or your QA testing crew, to make sure that things are done to a spec, and whatever spec that's being put on by the folks, your architects and POs, are being honored, and all the contracts are working as we expect it to. Now, what are the scenarios? The scenarios are, let's say the weather plays havoc in building a home. How do you respond? The parallels here is you have your system running, and there are a lot of different inconsistencies. I'm just trying to give two brief examples. Monitoring would be one that you'd want to invest in. So you would have to make sure that observability is being thought of not as an afterthought, but decisions are done right from the start of your whiteboarding on the architecture and how things are being built. So that is scenario number one. Scenario number two, weather caused a delay, but the project needs to be wrapped on time. What's the backup plan? So the backup planning, if that were to be the case of building a home, the construction company is probably going to add more resources, meaning more workers, right? So the same thing that can be done here. I mean, if things are the app is delayed, you got to, or you think the app is probably going to have periods where it's delayed, there needs to be planning for horizontal and vertical scaling on how when there's peak traffic or things like that, system auto scales, and there are temporarily available worker nodes or workers or whatever you want to call it, that would reduce the backlog, and then the traffic keeps flowing back and forth, and it's all a happy system. All right, that's the example and the scenario. All right, questions, guys? Does anybody have any questions?
Awesome. Thanks, Siva. I actually had a question.
Sure.
Going back to strong versus eventual consistency. And so I know for systems like etcd, one of the consistency it promises is that each read will fetch the most recent write.
Sure.
And I'm just trying to think through this. Like if you have a node that knows that it does not possess the most recent data, it goes to query its quorum to see who has the most recent data.
Sure.
And perhaps does a fetch to serve the client requesting that data.
True.
If it has to fetch it, and the client receives the most recent write, is that strong consistency or eventual consistency?
So strong consistency is, that would be eventual in my opinion. I'll tell you why. Strong consistent would be where the concept of one of the nodes having stale data is not there. Because what happens is, let's say you have a system where you are blocking the reads until the quorum is achieved on all the nodes. So you have a design where things are still NoSQL. You're not doing replication based on Postgres. You're using Mongo or something like that. Even Mongo has something like MongoS and MongoD where replication can be achieved. But to your question, if it's a backend where a node is capable of going out of sync and has to go to a quorum to get the latest data, that's an eventual consistent system. Because in a consistent system, you are a strong consistent system, you're guaranteeing the fact that no matter which data store I query from, the data is always going to be the same. So you would, in terms of architectural decisions, what you would do is, in a strong consistent system, if you have nodes that are out of whack, the reads would be blocked on that resource.
Okay.
Does that answer your question?
Yes. Yes,
okay,
it does.
Perfect. All right, awesome. Any other question, guys?
Hey, Siva. I have a question, particularly in the area of performance testing that you mentioned earlier. So clearly, the ideal is to design a system that is scalable.
Sure.
And at some point, you want to ensure that you can achieve a certain level of performance to that using that system.
Definitely.
If the system is large enough, my question now is, how do you test performance? Because what could happen is that the cost of running enough load through that system
Definitely
could eventually rival running your system itself. So
definitely, yeah.
Two ways I see this possible to do, and you tell me what your experience has been so far.
Sure.
One way is you say, all right, I have a fairly good idea that my system is linearly scalable. Therefore, if I test the performance of one node and I can increase the number of nodes, then I can assume to a certain level of assurance that I can scale that way. So I only need to load test one node.
Yeah.
Or you could go and say, well, I need to test the whole system. What has been your experience with that?
Definitely.
And what has been the approach to not get the costs go while just running, load testing on those systems?
Gotcha. Hey, awesome question. And thanks so much for bringing that up, because a lot of times what happens is the issue it boils down to is cost. Like, is the team or the vertical, are they able to afford an environment very specific? Identical to what we have in production. If that would be the ideal case scenario, right? If it happens, great. We can go to town, we can have all the fancy bells and whistles of the way we want to do our performance testing, and potentially match what we want in real time. But that doesn't happen all the time, right? So the way I have approached it is I try to divide the app into divide the capability of the app into factors. By that I mean, let's say you have a load balancer. We just talk let's talk maybe a simple setup. You have a load balancer, and then you have 3 nodes sitting behind, and this is pre-Docker, right? So you had everything deployed in cloud, but Docker was not used. Everything was on VMware. You did the RPM, and things had to be deployed to a webhead and that kind of a shop. So you have a load balancer, you have nodes behind it, and you have a data store and maybe like 3 nodes handling the data store. If you're not able to replicate the environment for something like performance testing, then the way you would do it is like something that you suggested. You try to explore the limits of a setup that is a factor of the production system. By that I mean, if we have 3 nodes deployed behind a load balancer and 3 nodes deployed behind the database master, what you would do is try and replicate an environment of a factor. So if that is, factor one, you could go to a 1/3 setup where you have a one node behind the load balancer for the API and one node for the database. And then you go for a 2/3 setup where you have two nodes sitting behind the API and two nodes behind the database, right? What you're trying to get out of that is you're trying to mathematically kind of like what's the word I'm looking for? There's a good word in math for that. But you're trying to extrapolate data based on what you currently have. So you would run your performance test, try to understand the limits of your existing setup, and then you would extrapolate the data to a factor of 3 or a factor of 2 based on what's being observed here. Because a lot of times, until you really know data about your target customer use cases, number of people using your system and things like that, you are still, that's where performance testing is more of an art than science, because you are trying to explore the limits of the system. So as a performance test engineer, my responsibility, I would think, if I were given such a setup, is to highlight what, based on the baseline tests you have done, what the system can scale to, and call out risks with the architect and the PO if that's not going to meet the spec with respect to the expected uses. Because a lot of times, it's not fair. I mean, I agree that a lot of things have to come from performance. I mean, the product owner, but it's not fair. Like, you're going to go to a product owner and ask him, hey, I know we are going to launch this tomorrow, and this is like the first thing that, the first launch of this specific product. I need you to tell me, what are the number of target users. He or she is not going to have a clue, right? I mean, if they do, they might probably make an educated guess, but that's never going to be the true accurate number. So for the more methodical way of approaching that, in my opinion, would be divide your app into factors in terms of infrastructure, and then if you have a production setup, try to do something that mimics half of that, 1/3 of that, and keep expanding your performance tests, the load and whatnot, to capture numbers of what happens on a 1/3 factor, 2/3 factor, or half, and then try to extrapolate the numbers to what you would eventually see in production. Did that answer your question?
Yep, it does. Makes sense. Thank you.
Perfect. Any other question, guys? All right.
I guess I have one more.
Sure.
Not a question, but just a comment, and I put in the chat here. If I'm correct, Thea was the one asking the question about consistency. That specific example, and I feel like her question stems from another question, which is, when you're talking about consistency, what is your frame of reference?
Sure.
If my frame of reference is a user, do I really care what the system has to do to give me a consistent answer? In which case you could say, well, it's consistent to me because as a user, I see the same data.
Yeah.
But if you go and peel one layer and then go to the service, now you have a different view, because now you're looking at the database and saying, okay, I don't have the data here. I have to go get it there. Therefore, from the point of view of the service, there is not like a strong consistency. So I don't know if that helps, but that's my take on the question and why.
Yeah, that's definitely a great point, because at the end of the day, it also depends on. So in this case, I would think it'll be more of the classical architect problem. Like, are you trying to do the right thing or do that thing right? So if you're trying to, if your frame of reference is do the right thing, it's probably you're targeting your customers because you want to build the right product. But if your frame of reference as an architect is do the thing right, then you got to make sure that you have the idea, but you got to put in place the right process to realize the vision. So, but yeah, great point. I agree. All right, any more questions, guys? I think I have maybe one more. Do I? There it is. Oh, yeah, I have the one more thing slide. Siva